Okay, tonight's homework we're going to be talking about empirical formulas from analysis. This is section 3.5 in your white textbook. And an empirical formula, we hopefully remember this from regular chem. If you don't, that's okay. Empirical formula is going to be defined as our lowest whole number ratio of atoms that are in a compound. And so I'll give you an example of what this is going to look like for, we have a compound called benzene, which is C6H6. And we'll talk more about benzene as the year goes along. Now, this would be called what we call a molecular formula, because it's not the lowest whole number ratio. To get to the lowest whole number ratio, we'd have to divide both by 6, and that would give us a CH, and that would be called our empirical formula. So, with that said, not all compounds have molecular formulas that are different from their empirical formula. Another example would be the molecular formula for water, which is H2O. Now, that is already in its lowest whole number ratio, so we would say that that's its empirical formula as well. The important thing about empirical formulas is they can tell us what's going on at the molar level. And so an example of that is water. Now, just by looking at that molecular and empirical formula, we know that we have 2 hydrogens per 1 oxygen. But another very important aspect of this is we can also say in a water molecule that we have 2 moles of hydrogen per 1 mole of oxygen, and that's where calculation of empirical formulas becomes very useful. We can use it to determine what an unknown compound is. Okay, what I'm going to do now is I'm going to show you how to calculate empirical formulas, and I'm going to give you this little flow chart. And this little flow chart will help us go from one step to the next, and we'll always know that if we can start at anywhere on this flow chart to get to our ultimate goal, which is to find our empirical formula. So that's going to be our last part of our flow chart. Now, what we're going to do is we're going to start on the flow chart way over here on the left, and this is if you're given a mass percentage. And we're just going to go through this really quickly. It'll make sense once we work a couple of problems. Now, if we're given mass percentage of something, well, the first thing we're going to do is we're going to assume that we have a 100-gram sample. And that might not make any sense right now, but it will soon. Assuming that will give us grams of each element. Now, once we know grams of each element, we need to do something to convert to moles of each element. Now, we know how to convert grams to moles. All we really need to get there is we're going to divide by molar mass. And we did that over the summer. Anytime you were given like 10 grams of oxygen and you wanted to convert it to moles of oxygen, you just need to divide it by 16 molar mass. And the last thing we're going to do, if we're given moles of each element, knowing the ratios that we talked about above in the molar level, all we have to do is divide by lowest number of moles to get a proper ratio. Now, I don't expect for that to make a whole lot of sense right now, but we're going to work a couple problems, and then we're going to use this little flow chart, and that'll help us get from one place to another. Okay, so if we're starting with moles here, we're starting with moles. The problem might ask us to calculate the empirical formula when we have 0.0130 moles of carbon, 0.039 moles of hydrogen, 0.0065 moles of oxygen. So using the flow chart, we can look above, and we're already given moles of each element. We're only one step away from calculating the empirical formula. So really, we're at moles. All we have to do is divide each one of these by the lowest. And so we have 0.01, 0.039, and 0.0065. So 0.0065 is the lowest number of moles of each. So we're going to divide everybody by 0.0065. So to get our carbon, we're going to divide that by 0.0065. It's the lowest number. 0.039 moles of hydrogen divided by 0.0065, and then obviously 0.0065 moles of oxygen divided by itself is going to equal 1. So we know the oxygen is going to be 1 mole. So on these other two, when I divide this first one, I get 2 moles of carbon. On the hydrogen, when I divide it, I get 6 moles of hydrogen. Everything came out nice and even numbers or whole numbers. We didn't have to worry about any decimals. We'll deal with that later. So this tells us that this empirical formula of this compound is going to be carbon 2, because we have 2 moles of it, hydrogen 6 moles of that, and oxygen 1, and we don't really need to write the 1. So C2H6O is going to be our empirical formula for whatever this compound is. Our next problem, we're going to start off with grams. And in this problem, we're giving 11.66 grams of iron and 5.01 grams of oxygen, and we're being asked to calculate the empirical formula. And so we look at that flow chart, and now we're over to grams. And so we want to do grams to moles first step. And then we're going to divide by the lowest number of moles after that. So let's do grams to moles real quickly here. And so we have 11.66 grams of iron. And we're going to divide that by the molar mass of iron, which is 55.85 from the periodic table. When we divide that, we get 0.2088 moles of iron in this sample. We're then going to go to our oxygen, and we have 5.01 grams of oxygen. 1 mole of oxygen, we're going to divide it by the molar mass of oxygen. Notice I'm not making this diatomic here on the oxygen because, well, in this case, it's just a single oxygen atom we're looking at. Then we're going to come out with 0.313 moles of oxygen. That's our first step here from that flow chart above. Number 2, now we're going to divide our lowest number of moles. And so you should be able to see easily that iron is the lowest number of moles at 0.2088. And so we already know that if we're going to divide iron by itself, we're going to get the ratio of 1 mole of iron. So I won't do that. And then for the oxygen, I'm going to go ahead and point 0.313 moles divided by 0.2088 moles. And I come out with an answer right about 1.5 moles. And so that gives us our empirical formula of FeO 1.5. And as you know, that is not a valid empirical formula because it's not the lowest whole number ratio. So anytime we come across this and we have a decimal, let's make an assumption here. We know Fe is 1. I'm going to go ahead and put a 1 in there. We want to multiply this number by another number that we can get to a whole number. And so what we're going to do is multiply this whole thing by the number 2. Now the number 2 works so well because it's going to take that 1.5 and turn it into a 3. But we have to multiply all the way through. So this 2 is going to distribute to the Fe. So we're going to get Fe2. The 1.5 multiplied by 2 gives us 3. And that gives us an empirical formula of Fe2O3. The last type of problem we're going to do for tonight's homework is we're going to get a percentage problem, where they've given us 40% carbon, 6.7% hydrogen, and 53.3% oxygen by mass, and we're going to take this and convert it all the way over to the empirical formula. So on the flow chart, the first thing we're going to do is we're going to assume that we have a 100-gram sample. And by doing that, all we do is we convert, because if I had a 100-gram sample and 40% of it is carbon, that means that we would have 40 grams of carbon, basically is all we're doing. So we have 40 grams of carbon, we're going to have 6.7 grams of hydrogen, and we're going to have 53.3 grams of oxygen. First thing we do. Now, once we do that, we're now into grams, and we're going to do a grams to moles conversion. We know how to do a grams to moles conversion. All we have to do is divide by molar mass of each one of these substances. 12.01 for carbon, 1.01 grams for hydrogen, 16 grams of oxygen. By doing that, that's going to convert each one of these into moles. We're going to get 3.33 moles of carbon. We're going to get 6.63 moles of hydrogen, and we're going to get 3.33 moles of oxygen. And I like those numbers because we know when we divide them, they're going to come out nice and even. So we divide by the lowest, which is 3.33. So we already know carbon's going to be 1, and oxygen's going to be 1. And then we have that hydrogen, which is 6.63 divided by 3.33, but you know what, that's going to give us right about 1.99, which I think we can safely round up to 2. And so our empirical formula, C1H2O. And that's how we do empirical formulas. So for tonight's homework, you just have to take notes on this, all 3 pages that we've had, and have them in class tomorrow. We'll stamp them, give you credit for taking the notes, and then we'll do some practice problems tomorrow in class. Hope you all have a nice evening.